Okay, so if we remember back to Niels Bohr, what he said about the atom was that there is a nucleus in the core, and then there are energy levels where the electrons travel. Energy level 1, energy level 2, energy level 3, and that electrons can be located in one of those specific energy levels but nowhere else. Kind of like the rungs of the ladder. You can be on the first step or the second step or the third step, but you can't be halfway between the first step and the second step. Okay? So what Bohr said was they must be in these discrete energy levels. Okay. And so his model was based on what he saw. Where if you take a gas, let's say in this case it's helium, but you could take hydrogen, and if you energize it, and you can energize it, this uses a high voltage, but you can energize it with light or electricity or fire. And then you look at it through a prism, that what you see is these thin lines. We call it the energy emission spectra. You see these thin lines and not a full rainbow like you would expect. Okay, so you know a prism will separate light, and when the light passes through it, you see a rainbow of colors, just like you would on a rainy day when it's sunny out and you see a rainbow in the sky. What's happening is the light is being bounced off the raindrops, and you see that it actually separates the light into its colors, and you see the broad spectrum. So he wanted to know why, when he energized hydrogen in particular, and he looked through the prism, what they captured was these thin lines and not a full spectrum. Okay, so before we can talk about his explanation, we need to talk a little bit about light. So light can be considered to be either a wave or a particle. So for waves, this is a wave. It's got a crest and a trough. The length of the wave is the length from one crest to one crest, or one trough to one trough. It's got different amplitudes or heights, okay, and different frequency. Frequency is how often it goes by a certain point in a certain amount of time. So this is a relatively low frequency compared to a high frequency, up and down and up and down, up and down, right? So long wavelength, low frequency, high frequency, short wavelength. So they're inversely proportional. Okay. So there are two important relationships. You need to know that as wavelength gets bigger, as my waves are bigger, my frequency is lower. Okay? So the relationship is inversely proportional, and the relationship actually can be defined as C equals lambda nu. Lambda, so C, first of all, is the speed of light, which is defined as 3 times 10 to the 8th meters per second. Really, really fast. As fast as what physicists have said could be possible. Means you could go around the Earth 7 times in a second. Very, very, very fast. Lambda is the wavelength of the light, and nu is the frequency of light. Okay? So the speed of light is always the same. So if your frequency is high, your wavelength must be long. And if your frequency or your wavelength is low, then your frequency must be high. Okay, so they are inversely proportional. But frequency and energy are directly proportional. So as I increase the frequency of a wave, I also increase its energy. Okay? So a wave like this, you imagine the up and up and down, up and down, high energy compared to these slow lumbering waves, which are going to be low energy. Okay, so light is, there's a lot of different types of electromagnetic radiation or light, and the ones we can see, the part of the spectrum that we can see is very, very narrow. It's called visible light, and it's just this small range from 700 nanometers to 380 nanometers. This is what's called visible light. And within that range, we go from a low energy or a low frequency of red, 700 nanometers, to a high frequency, high energy, short wavelength of blue. And you can think about blue is going to be higher in energy, just like a blue flame. It's going to be hotter than a red flame. Okay, but there's lots of other electromagnetic waves. Radio waves are huge. They are like more than football fields long. And then on the other extreme of really high energy, high frequency waves, you have gamma rays. These are the kinds of waves that come off a nuclear reaction and generate all that energy. Okay. All right, so what Bohr said was, this is what happens to an atom. So if an atom gets energized, and we said that can happen with heat or light or electricity, what happens is this electron moves from its normal ground state, its low energy state, to a higher energy level. Okay, it jumps. Can't jump in between, so it's going to jump to this level or the next level. And that what happens is once it's up there, it always wants to come back down to its ground state. And when it does that, that extra energy it had has to go somewhere. And in fact, it gets released as colored light, also known as a photon. A photon you can think of as a particle of light. Okay? So it's not the energizing when it jumps to the excited state that causes the spectrum. It's the return to its ground state that releases the energy known as a photon. So why are there the different colors? Well, you can imagine, let's say you have an electron that jumped from its ground state one energy level. When it returns to its ground state, it's going to release some wavelength of light, let's say the red. Okay? If this same electron were to jump 2 energy levels and then on its fall back, this is a higher difference in energy, so it's going to release light of a higher frequency, so more likely to be blue. And if it, let's say it jumped 3 or more levels, when it falls back to its ground state, it's going to release even higher energy light, and let's say that's going to be the violet. Okay? So the difference between the lines is the difference in the energy or frequency of that light that comes off based on how many energy levels the electron is moving. So what's wrong with Bohr's model? Well, big problem with it is it only works well for hydrogen. Although his model is no longer accepted, there's big parts of it that are, and he really helped move forward the atomic theory almost to where it needed to be. Okay. So today we believe in something called the quantum mechanical model, also known as the electron cloud model, and it looks like this. So there's the people associated with it are Erwin Schrödinger and Werner Heisenberg. And what Heisenberg said was he's credited with what's called the uncertainty principle. He said you cannot know exactly the location and the speed of an electron. So all you can know is the likelihood of where you would find it, the probability. So Schrödinger put together these complex mathematical equations to solve for the likelihood of where electrons would be located. Okay, very complicated equations. Okay, so the Heisenberg uncertainty principle says it is impossible to know exactly both the velocity and position of a particle at the same time. Okay, so let's go back and watch that again. Alright, so before collision, we have a photon that strikes an electron. If you're looking at something, the only way you can see it is if light strikes it, okay, and bounces off. So what we're saying here is that when light hits it, the process of viewing or light hitting it causes this electron to move, and the wavelength changes coming back. So the process of just viewing causes movement, is what Heisenberg says. And therefore you cannot know both the speed or velocity and the position of the electron. So you can never really know where the electrons are. But what Schrödinger said is you can predict the likelihood of where they're found. So here's a complex equation known as Schrödinger's equation. And if you take these and solve them, you end up defining the orbitals where electrons are most likely to be located. So if we just go back for a second, so this area of dark blue would be an area where you are more likely to find an electron than in the area has less dots. So the fewer the dots, the less likely it is to locate an electron there. So you could find an electron here. It's just not very likely. You can find an electron here with high probability. Okay, that's what his equation does. So if you solve for his equation, it ends up graphing out these different shapes of the orbitals where electrons are considered to be located. And one of the quantum numbers you get is this shape of orbital. S is a spherical shape. P is kind of like a figure 8. A D has lots of different shapes. This is just one of them. And P's also have different shapes. But what you solve for in Schrödinger's equation is what's called 4 quantum numbers. So each electron has a unique address based on those 4 quantum numbers. The first quantum number is the energy level, and this correlates with the shell that the electrons travel in. N equals 1, 2, or 3. The shape of the orbital, whether it's an S, a P, a D, or an F. The orientation, so if I have a p orbital here, this might be the x-axis. I'd have another one here on the y-axis. And then, I would have a third one coming at me, which would be the z-axis, okay? And then the last is, within a given orbital, I'm going to have up to 2 electrons, either 1 or 2, and they're going to have opposite spins. So if we want to take a look at very simply the difference between Bohr's model and the quantum model. Bohr said electrons travel in these very specific energy levels around the atom, whereas the quantum model says can't really be sure where the electron is, it moves, and its likelihood of where it's going to be found will vary. Okay. Alrighty, so then do it for us now, and then the next podcast we'll talk about electron configurations.